Okay, so the last thing that I have to talk about is related to the organization of this course. So we are heading to the end of the introduction module here, where we covered what is explicit solid dynamics. We talked about a possible way of classifying dynamic events according to the impact velocity. We saw industries and applications where explicit solid dynamics may be useful. I shared with you from my own personal experience what are the skills that I consider important for engineers aiming at positions of simulation engineers, specifically related to explicit solid dynamics. I shared with you some of recommended references, and now we're talking about the organization of the course. Okay, so then we have another two modules, and module 1 covers the theoretical aspects of explicit solid dynamics. So in this module, we start with a review of nonlinear solid mechanics, covering kinematics, stress measures, dynamic equilibrium, conservation, stress waves in solids. And then we move on to the numerical aspects of explicit solid dynamics, with a main focus on the time integrator. So we will see the differences between explicit and implicit methods. We'll derive explicit time integrators, the central difference method. And then we will focus on the numerical stability of explicit time integrators. So this is a very foundational module where we will be mainly focused on the theory. And this is essential for moving on to module 2, where we cover the practical aspects of explicit solid dynamics. So in module 2, although we are talking about practical aspects, we will not be using one specific software. We will be talking about core concepts that are applicable to any software of your choice. So we will be talking about consistent unit systems for dynamic analysis, meshing techniques that are successful in explicit dynamics, problems such as the hourglassing that may appear in your explicit dynamic simulations, speed up techniques such as the mass scaling, or also we will be talking about some constitutive models for hyperelasticity, the Nell-Hookian model, or for elastoplasticity, the Johnson-Cook hardening law. We will see some best practices in contact and impact analysis. We will understand what is and how to apply the smoothed particle hydrodynamics meshless technique. Then we will talk about post-processing transient dynamic models, having a look at the energies and conservation properties of your model, this type of thing. And finally, the topic of parallel and distributed computing, that is really important once your models start becoming larger and larger. So this concludes the introduction module. I hope you enjoyed what you saw. Hope you learned something and also became interested in learning more. So you can join me in the theoretical and practical modules, and I will see you there.